Alright, in this second video we're going to now actually formally define work. Consider our block again from the first video where we have a force here, say pulling upward, and the block is displaced along the table some amount. Now we're going to let that displacement be very small, and the reason for that is that this force arrow over time might change, or this angle between them might change. In other words, a person might quit pulling up and start pulling backwards or something. So we're going to make it so that the path that we follow is so small that none of that can happen. How small does that have to be? Well, it could be absolutely go to almost no path, in which case we need a more advanced math called the calculus. In this particular course, we're not going to have that. We will say that they go some finite amount. It might be 0.001 meters, but it's still some small amount. And if it does change, we could always use a spreadsheet or something to add up the thing. In most of your problems, what it'll do is we'll break the problem into straight line segments, where you move some distance in a straight line, and then maybe if you're going to go to, you might go a different path in another straight line. Now, the definition. If these vectors are written in polar form, it's easiest to say it follows this definition. Simply take the length of the first vector, the force, multiply by the length of the displacement vector, which I call delta x. Take the angle between those two vectors when you put the vectors tip to tail. In other words, here's delta x, there's f, put their tails so that they touch right here. Find the angle between those two vectors, and that's the angle that's less than 180 degrees. Not the big outside angle, the in angle. Alright? Find that angle and take the cosine. It turns out it doesn't really matter here whether you use the in or out, but it will later on when we come to another operation called the cross product. This is a number. Maybe it's cosine of 60 degrees, which is 1/2. This is a number. Maybe that's 2 meters. And this is a number, 5 newtons. Multiply those three numbers together. When you do that, you're going to get a number, a scalar. That scalar number is called the work. We said it's delta W because it's just a small change in the work based on this small change in the path. Now, the question, of course, is what does the work tell us? What the work is going to relate to is the speeding up or slowing down of an object. If the work is greater than 0, the object is speeding up. If the work is less than 0, then this force is causing the object to slow down. And if the work is 0, then this force has nothing to do with changing the speed. Now, it turns out that there may be many forces on the problem, so we're going to have to add up the works by all the forces to determine whether or not the whole effect is to speed it up. Some may be trying to speed up the block, some may be trying to slow it down. We'll get to that in a little bit. The main thing is just to be able to use this formula. Now, this special formula is actually a special case of what's called the dot product. So I've also written the dot product over here, which is the more general way to write it. It says take the vector f and dot it, which is a special type of multiplication operation, into the displacement. We talk more about the dot product in this math in another video. You should watch those videos because it's not always the easiest form to do a problem in polar form. That is where you have the lengths and angles. Sometimes it's easier to work problems in Cartesian form, as we found out when we added vectors vectorially. So you should be able to do it either way. Go watch the dot product videos if you haven't already. Now, let's look at this definition and our previous examples. In our first example, in the previous video, we had an object, the force was going like this, and the displacement delta x was in the same direction. In this case, the angle theta was equal to 0 degrees, and the cosine of 0 degrees is in fact 1. So all we ended up was force times this distance, which is delta x. And this was greater than 0, so the object sped up. In the second example, the force that we were applying was down, and delta x was horizontal. In this case, the angle was 90 degrees, and we know the cosine of 90 is 0, so no work was done. The object did not change speeds. And in the last example from the first video, we had the force going this direction. We had the displacement going this direction. So in this case, the angle between those two, this angle, is 180 degrees. And the cosine of 180 degrees is -1. So we get negative force times displacement, and therefore the work is negative. And when you have a negative work, the object slows down. So we have two vectors. They multiply together, but they do not produce a vector. They produce a number. And that number tells us something about whether the object is going to speed up or slow down. What it really tells us is what's going to be called the change in kinetic energy, assuming that I've added up all the forces and all the works. All right? So there's something about speed that's going to come into that. We'll develop that a little bit later on, but what I want you to know now is that a force is attempting to speed up or slow down an object based upon its work. If it does positive work, it's trying to speed the object up. If it's doing negative work, it's trying to slow the object down. And if it does no work, it is not affecting the speed of the object at all. All right? And if it does no work, and we're going to count up bank accounts, that is work bank accounts, just like checking and savings, but they don't have money in them, they have work in them, if you would, then if we find that a force is doing no work, we don't even have to care about that force in the problem. We can just throw it away. Now, our physicists will get upset with my term work bank accounts. They would prefer to call these energy bank accounts. But it's good enough for the level of physics that we're teaching here, and in fact it's probably good enough in all the way through undergraduate school, even if you're a physics major. So we'll come back and talk about some of the more deeply underlying philosophical issues later. Right now, let's just see if we can calculate these things. What is the unit of work? Well, the unit of work should follow from the units of the things that we had, and we had a force which was in newtons and a displacement in meters. So you might think it's Newton meters. It is not. And the reason for that is there's another physics quantity that shows up in these problems, and it has the same units, Newton meters, but it's a vector, and it's more like what's called a twisting type force called a torque. So because we don't want to mix those up accidentally, we've given the unit of work a different name. When you're talking about work, then we call that a joule. Now I know that when you do dimensional analysis, a joule is equal to Newton meters, but we do not write Newton meters when we're talking about energy or work because we don't want to get them mixed up with torques. This was named after James Prescott Joule. He's an interesting guy, interested in trying to help the family business, which was basically a brewer. He made beer. So you should go read about his history and his idea of the conservation of energy. All right. Now, to evaluate work, in general, to evaluate work, you're going to have three things. You must have a force acting on the body. If there's no force, then the no force can't do no work. You must have a displacement of the object. If the object is not displaced, if the force doesn't act on the body over some distance, then you can't have any work. And last but not least, a component of the force has to be along the displacement. If the force is perpendicular to the displacement, it does no work. There are three requirements. And before you can calculate a W, you must identify these three things. Now, what we're going to do is do some examples in the next video to help show you how to do these type of calculations.